Welcome back. In this part of this chapter, we're going to go deeper into calculations to be able to determine if a reaction is reversible or irreversible. And we're going to do that using the entropy of the universe. Remember, if the entropy of the universe equals zero, which is the entropy of the system plus the entropy of the surrounding, then the reaction is reversible, is in equilibrium. If the entropy of the universe is more than zero, a positive number, then it's an irreversible process. And that's because they are spontaneous. If it's less than zero, then it's a non-spontaneous reaction. And the system that we're talking about in this case is the actual chemical reaction. So we're going to be using, like I said before, free energy exchanges to predict the reaction is spontaneous or not. That would be delta G. We're going to see how temperature affects a reaction being spontaneous if the enthalpy and the entropy are given. And we're also going to be able to calculate the Gibb free energy using the enthalpy and the entropy. So this should be a very short presentation. So let's begin with this. Given the values of enthalpy of the reaction, entropy of the reaction or entropy of the system, and the temperature, let's determine the entropy of the universe. And the entropy of the universe is going to be the change in entropy of the system, in this case the reaction, plus the change in entropy of the surrounding. And remember, we know that the change in entropy of the surrounding equals minus delta H of the system, in this case, the reaction, right? Since we are looking at the reactions, that's the system, divided by the temperature, which had to be on Kelvin, from 0 to whatever temperature. And we know that if the delta S of the universe equals 0, then it's reversible. If it's bigger than 0, then it's irreversible. So let's see what we have. Delta S of the universe is going to equal delta S of the system, which is the reaction. So that's going to be positive 253 joules per Kelvin, plus delta S of the universe, which is going to be the minus enthalpy, which is minus 125 kilojoules, over the temperature, which is 298. Since this is given on kilojoules, let's go ahead and change this to kilojoules, which is going to be just divided by 1,000, right? So obviously, negative times negative is going to be positive. So question is, would it be equal to 0? No, it's not going to be equal to 0 because you're going to have a number plus another number, and both of them are positive. So this is going to be irreversible. So there's no need to actually do any calculations. Whatever numbers we add, it doesn't matter how small they are, they're going to be positive, so it's going to be bigger than 0. So that's going to be irreversible. So once more, important to remember, entropy of the surrounding can be found using the enthalpy and the temperature. The entropy of the universe tells us if a reaction is spontaneous or not. If it's equal to 0 or bigger than 0, then it's spontaneous. And if it's spontaneous equal to 0, it's going to be reversible. Bigger than 0, it's going to be irreversible. And remember that you have to take into consideration that negative times negative is positive, positive times positive is positive, negative times negative is positive, negative times positive is negative. So keep that in mind. So with that in mind, go ahead and do those two problems. And we can move to the next topic, which is going to be given the values of enthalpy, entropy of the system, and the temperature, determine the Gibbs free energy. And the Gibbs free energy bigger than 0, non-spontaneous forward, so from left to right, delta G of the reaction less than 0, spontaneous, going from left to right as presented, delta G of the reaction equal to 0, that means it's on equilibrium. So very soon we're going to start seeing how the equilibrium constant relates with these thermodynamic quantities also. So let's calculate that. And we also know that delta G of the reaction is going to be equal to delta H, or enthalpy of the reaction, plus T delta S of the reaction. So let's see what we have here. On this case, we're going to have delta G of the reaction is going to equal minus 125 kilojoules plus 298 Kelvin times 253 joules over Kelvin. Always write the units so you can see that you're not done yet. Those two have to match first. So this is going to be 0.253 kilojoules. And you already know how to do that from Chem 1. So when I do that, $298 times 0.253 positive, that's going to equal 75.4 kilojoules. And we adding these to minus 125 kilojoules. I can already see that my result is going to be negative, so this is going to be spontaneous. That's all I need to know. Would it be negative or positive? From those numbers, I know it's going to be negative. The negative is the bigger number. So that's going to be spontaneous. So with that said, no need to do the calculations. From that said, go ahead and do those two problems. If you don't do the calculation, you have to explain how you know it's spontaneous. And with that said, we now know how to use the free energy, or delta G, to predict if the reaction is going to be spontaneous or not. Less than 0 is spontaneous. Predict the effect of temperature on spontaneity given delta H and delta S. So when we did this problem, the temperature here, if it's really big, the number becomes really small. So that can affect if you're going to get positive, negative, or 0. So that's how the temperature is going to affect the entropy of the universe. And then if we know the enthalpy, and we know the entropy and the temperature, can you find delta G? And that's the last problem we did. And with that, we're done with that part of the chapter. We only have one more section to go. So the last 3 chapters on this, from this textbook are the easiest one, in my opinion. So we're moving kind of faster now because they're easier and shorter. But practice like anything else. So see you next time where we're going to be finishing the chapter.